All right, so this is the last lesson in the entire course, looking at the probability and statistics and looking at something called Markov chains and coming back to matrices and the idea of a transition matrix, which we'd actually seen earlier in different scenarios. Let's just get straight to here. So this diagram here, called the transition state diagram, shows you how the probability of three different states relate to one another. And so, for example, if it's, let's focus on it being sunny, let's be optimistic. If it's sunny right now, we can see there's a 60% chance it'll be sunny tomorrow, a 15% chance it'll be rainy tomorrow, and a 25% chance that it'll be cloudy tomorrow. And we can, that's how we read this sort of diagram. And so, just to make sure we know how to read it, first ask for the probability of it being sunny given that it's rainy. So we have this conditional probability here. So this is a given, it's rainy, which means in this case, I could just look right here. So we know it's rainy. What's the probability that tomorrow it's going to be sunny? Well, all I got to do now is look here. Okay, if it's rainy, then I can see right here, there's a 25% probability. And that's it for that. So this is 0.25 or 25%. All right, so I can summarize all these different possible probabilities with a matrix, a 3x3 matrix, because there's three different possible states here. And while we have some choices in general for this matrix, which I will call matrix T, our columns, those refer to the states now, the present state, and our rows, these refer to the future states, like tomorrow in this case. So if I look at my diagram, I'm going to set it up with, get this kind of set up here. My three states are sunny, rainy, and cloudy. And so I'm going to write that up here. I'm going to have sunny, rainy, and cloudy. And that is for now. That's for today. That's the present state. And so I now need to have three rows that'll represent the future state in the same order. So my first row will be sunny, second row will be rainy, third row will be cloudy. And again, this is for tomorrow. 1M in tomorrow. 2 R's. There we go. And so now, right here, this represents the probability that if it's sunny today, that it'll be sunny tomorrow. And so I look right here. If it's sunny today, the probability that it'll be sunny tomorrow is 60% or 0.6. Below it, this is the probability if it's sunny today that it'll be rainy tomorrow. So looking back here, if it's sunny today, the probability it'll be rainy tomorrow is 0.15, 15%. Oh, not yet. There we go. And then lastly, in this column, this is the probability that if it's sunny today, that it'll be cloudy tomorrow. And I'll do one more before I just show all the rest. So if it's sunny today, the probability of it being cloudy tomorrow is 25%. Now, before I just quickly show the answers for the rest, if we are correct, each of these columns should always add up to 1. Good way of checking if you're coming up with 1, just make sure every column adds up to 1. So that's looking all the probabilities if it's sunny today. So then rainy and cloudy, same idea. I'm not going to go through every example in the diagram. You should get for rainy first 0.25, 0.45, and 0.3. And then cloudy should be 0.3, 0.35, and another 0.35. So just to make sure we understand these, if I just look at this very last one, that tells me there's a 35% probability that it'll be cloudy tomorrow if it's cloudy today. Okay, so that's the transition matrix. And we should be able to go, if we're given this, we should be able to draw something like this, or if we're given a diagram like that, we should be able to go to the matrix. The actual order of the sunny, rainy, cloudy is up to me. Just keep in mind the order of the column should match the order of the rows, but we know by convention we do want to realize that the present state should always be up here, which are columns, and the rows are the future state. All right, I'll call this matrix T. And so I've created the first part. I want to use this now to determine the probability of it being sunny 3 days from now, should it be raining today. And so I can actually find this out quickly if I just take this matrix 3 and raise it to the power of 3. And which on a GDC I can do very, very quickly. And I will, on my GDC, I will get a 3x3 matrix with lots of fairly messy values. The key is, which value do I want to look at? I want to look at if it's going to be sunny, if it's rainy today. So I'll be looking at, that is this value, which is row 1, column 2, so right here. If it's raining today, what's the probability it's going to be sunny in the future? So in 1 day from now, it's 0.25, but I need to multiply this matrix by itself 3 times, the square matrix. And if we do that, that value right here should end up being 0.3885. 3885. And so the probability that it will be sunny in 3 days if it's raining today is approximately 38.9%. All right, and keep in mind that was on the transition matrix raised to the power of 3, that was row 1, column 2. All right, so now I have a matrix given to us, a 2x2 transition matrix that's looking at how the probability of people, or you almost think of the percent of people who arrive on time today compared to will they be late or on time tomorrow. And we have this matrix here. And using this matrix, they predict that tomorrow there'll be 640.32 people, is this on time? Yeah, on time tomorrow, and 335.68 late tomorrow. Or it will be late tomorrow. Keep in mind, one thing that's helpful, it doesn't actually tell you directly here, but if I add these up, that tells me the total number of employees, and we get 976. So there's 976 employees in total. So in this case, we know the future prediction, how many are there now today? And so one way of approaching that is to take that transition matrix right here. I'm going to copy it down right here. So take my matrix, which is given to us. And so the idea is if I take this matrix and multiply by 2 values here, then I'll get a new column matrix that tells me the values for tomorrow. But we know those. We know that tomorrow it's going to be 640. I need a bit more space here. 0.32, and this is 335.68. So in this case, we know the future value. After 1 day, we don't know the present value. So to find this, I can just call this x and y, and let's solve for x and y. I can just solve this really quickly using a system. If I look at this here, this lends itself quite nicely to a 2 equation, 2 variable system. Just think about matrix multiplication. If I look at this right here, the first step would be 0.95 times x plus 0.07 times y equals this. And I get a system of equations quite quickly. And there's lots of choices. You could also use matrix algebra to solve this, but it's probably fastest just to solve a system and use your GDC. Keep in mind with matrices, we always want to realize how they can connect to systems, and we should really quickly get 2 values. X equals exactly 650, y equals 326, 326, there we go. And keep in mind this represents, that means there were 650 people on time today, and 326 people late today. That's a lot. Traffic must have been bad. All right. That said, if I wanted to find how many people, now that I know how many people to start, if I raise this to the power of 2, the transition matrix, that would tell me this value here would tell me how many people we predict to be late in 2 days from now. All right. That's it. I won't change the question anymore. However, I then ask for the steady state vector and state its significance. So a steady state vector in general is, if we take a transition matrix, raise it to a power, or actually I'll adjust this slightly. There's a few ways of explaining it. I'll start with this. Our steady state vector is if we take I'll go like this, our transition matrix, raise it to a power times some starting amount. As n approaches an infinitely large number, this tends to converge at a set vector. If we're thinking about, for this question, over time, this value here will represent over time, how many people do we expect on a given day to be late or on time? So one approach to this is to just take what we had before. We have our transition matrix already, right? That was given to us right here. We now know our starting amount, right? We can think of this as S0 or S0 and just pick a big number. And so I'm gonna, if I just do this and just use your GDC, now, there's only so big you can make it. For example, in my GDC, you can make n equal 200, make n equal 250. I think that's about as big. I can't get much bigger than that. If you try to make n equal 300, I think your calculator gets mad at you. But you notice as you put really large values into n, you start to see the same values over and over again. And so one approach here, which is fairly quick, is just we have our initial amount. Remember, that was from the last question. 650 and 326. We always had our transition matrix. Just pick a big number for n, and we should get to Sn equals, it sure looks like 569.3 repeating and 406.6 repeating. I say it sure looks like that because you can't actually tell because the values of my calculator aren't exact, and I will talk about how we can get exact values if we really want. That's it. What does this represent? This represents, over time, about 569 people each day will be late, and 407 people each day will be late. That's what it's telling us as we go far into the future. That's it. There is another approach to this that can give us these exact values with maybe a bit more confidence, but it is more work. And if we don't need exact values, or even if we do, we can get a pretty good sense by picking a big number here. However, that other approach I'm going to talk about for this last question. So here I have, again, a transition matrix, a 3x3, looking at 3 different cab companies, alpha, beta, and then a new one, gamma, the disruptor who's coming in. And it says currently, alpha cabs has a 50% share, beta cabs has a 40% share, and then the new upstart gamma cabs, very creatively named, has a 10% share. And we have, with this matrix showing us how month by month the shares are changing. All right, so I want to find the exact values. So that gives us a hint that I don't just want to punch in big numbers into my calculator. For the long-term market shares of these 3 operators. Right now, it's 50%, 40%, 10%. But over time, what will be the long-term share? So to kind of get it set up, I'm going to take that same matrix, and you got to excuse the boredom of watching me write down 9 decimals. Maybe it's enjoyable watching me write down decimals. All right, that's my transition matrix, right? This is like T. I know if I multiply this by, if I want to find the long-term value, then I can come back to this idea, which I actually mentioned in my notes. Where are they? Right here. Your steady state vector is the equivalent of taking your transition matrix, multiplying by some vector that ends up at the same point. By that, instead of having to raise it to a really big power, keep in mind if it's always going to converge towards a certain number, well, then if we can just find what that is from the start, it just won't change. So if I can solve something like this, I can get to my answer without having to just pick some big number. It may be a bit more work, but it's also something we should understand. And so if I take the idea of going T times Q equals Q, Q being what we're trying to figure out, or in this case, I can say my transition matrix times X, Y, Z equals X, Y, Z. So what's X, Y, Z is what we're trying to figure out. And the idea being I don't need to take this and raise it to a big power, because if I can actually find out what that steady state vector is, if I can actually start with that long-term amount, and then it just won't change. That's the idea. If we already start with what it's going to end up at, well, then it just will never change. So how can we solve this? Well, I can create a system. And using matrix multiplication, for example, 0.85 times X plus 0.05 times y plus 0.01 times z should equal x. That said, that equation is not wrong, but I want to adjust it slightly. Because if at some point I'm going to deal with a system, it's kind of nice if my system just equals a constant instead of my system having x on the left and the right-hand side. It's not difficult to subtract x from both sides, and I get a slightly more conventional and pleasant form of this equation. If I subtract 1x from both sides, I get negative 0.15x plus everything else the same on the left-hand side. And on the right-hand side equals 0. And so that's actually going to be more useful to me. I want to do the same thing for the rest. 0.05x plus 0.8y plus 0.01z equals y, but then subtract y from both sides. And if I do that, I should get this if I haven't made a mistake. I hopefully haven't. And then same thing for the third one. 0.1x plus 0.15y plus 0.8z equals z. Subtract z from both sides. And I get this. All right, that said, there's really one more equation I need here. Because if I look at just these three, this won't be quite enough to solve it. I need one more equation. And that is knowing about how x, y, and z all relate to each other. So what are x, y, and z? They're the market share. They're essentially the percentage of the overall market they have a share of. And currently it's 0.5 for alpha, 0.4 for beta, 0.1 for gamma. That's currently, but I don't know what the long-term share is, but I do know they must add up to 1. I do know that x plus y plus z must equal 100%. Or I can say x plus y plus z must equal 1. I know that. And so now I have 4 equations with 3 variables. I can now solve this pretty quickly by solving a system. GDC is extremely helpful for this, so let's solve the system. And your GDC should be able to do it quite quickly and should be able to give you exact values. In this case, we get x equals exactly 10/29, y equals exactly 8/29, and z equals exactly 11/29. So what do these mean? This is the alpha cabs share. This is the beta cabs share. And this is the gamma cabs share over time. So notice over time, it looks like gamma cabs will become the dominant force in here. Okay, that is the highest amount. That said, before I just kind of finish off, you could approach this like we did in this question, in which I take this transition matrix, multiply it to some big number, right? As n approaches infinity, there's only so big your calculator can handle, starting off with the initial amount, 0.5, 0.4, and 0.1. And as you get larger and larger numbers, you'll see numbers that come closer and closer to these values, but they may not be exact. And because I asked for exact values, that's why I want to approach it this way. Whereas for this question, it was probably faster just to do this. Although again, I could have done something similar. Could have solved the system and I could have set it up the exact same way. Some tough stuff, but finishes the unit, and that's kind of nice. So I can be quiet now.